In this section, you're going to learn how to avoid the formal mathematical definition of the derivative. So you should not have to use this anymore. In fact, everything we do in this chapter will now be avoiding the definition of the derivative. We're going to start with a basic rule called the constant rule. This rule applies for any numerical value, so any constant we call c. But before we go any further, I want you to notice the new notation that I'm using, the d over dx. That just represents the derivative in a different way. It's saying the derivative of whatever's inside the brackets. So here it says the derivative of a constant equals 0. Just to illustrate why this is true, let's look at an example of a constant function, y equals 3. Think about all the tangent lines that would lie on top of the line y equals 3. All of them would be flat, meaning they'd all have a slope of 0. And since the derivative is the slope, all constants have a derivative of 0. The next rule is our most important and we'll use throughout the chapter. It's the power rule. The power rule says that whenever you have x to any power at all, what you need to do is drop the power down to the front and subtract 1 from the exponent. Let's look at some examples just to show how that works. So for example, y equals x cubed. The derivative, y prime, would drop the 3 down in front. The new exponent would then be 1 less, 3 minus 2, or 3 minus 1, or 2. So the derivative is 3x squared. Sometimes, like in the next problem, we don't have an exponent, so the problem needs to be rewritten. Before we even get started with the problem, I'll need to rewrite this in an exponent form. You practice this in your summer assignment. This function is equal to y equals x to the 1/3. Same exact thing. So now I can actually use the power rule. The exponent will drop down in front. I'll subtract 1 to get negative 2/3. One more note. In this assignment that we do tomorrow in class, we'll actually practice getting in a habit of writing exponents without negatives. So this one can be rewritten as 1 over 3x to the 2/3. Again, we want to get in good habits of writing these answers without negative exponents. Okay, the next one. This one also needs to be rewritten. There's no rule so far for fractions. I'm going to rewrite this one with a negative exponent. Y equals x to the negative 2. Again, this was something you practiced in your summer assignment specifically for this task. Okay, according to the power rule, negative 2 drops down in front. I'm going to subtract 1 from that exponent. It used to be negative 2, and after subtracting 1, I get negative 3. This is a negative exponent, so it needs to be rewritten just like the previous example. Negative 2 is just a number, so it stays on top, and x cubed goes to the bottom. The last one is an interesting case. It's just plain old y equals x. So we have to really think about that exponent as being a 1. Same rule applies. The power, 1, drops down in front, and we subtract 1. What makes this so special is the new exponent is actually 0. Now, anything to the 0 has a special property. Do you remember what it is? If you thought 1, that was correct. X to the 0 power equals 1, which means the derivative itself is 1. This is so important and comes up so often that we actually want to remember this as a special rule. We'll think of it as a special case. So anytime you see the derivative of x, we'll rewrite it as a 1. So you shouldn't have to go through that notation of dropping the 1 down in front and subtracting. Just write a 1 in its place. The next rule is the constant multiple rule. This is going to help you remember what to do whenever there's a number, a constant, in front of a function. What this rule says is that you can completely ignore the constant that's in front and multiply it by the derivative of the function. So let's look at some examples here. 4/5 in this first example is the constant, so I'm not going to pay any attention to it. I'll start just by doing the derivative. Okay, 4/5 stays right in the problem. And now I'll do the power rule with the remaining variable. 2 comes down in front, and I'm going to subtract 1 from the exponent. The constant multiple rule tells you to multiply those two values together. So this answer is going to be 4/5 times 2, or 8/5 x. The next one needs to be rewritten. We don't do fraction bars, remember. So this could be rewritten as 2x to the negative 1. Notice how I still wrote a regular y equals. That's because I haven't done any calculus yet. Until you actually take the derivative, don't use the prime symbol. Y prime will happen whenever the negative 1 goes down in front of the 2. So it's going to drop down here, multiply with the 2 to get negative 2. The new exponent will be negative 1 minus 1, or negative 2. Remember, there's a negative there, so that should throw up a red flag to you. I'm going to rewrite this with a negative 2 on top and x squared on the bottom. The next one has a radical in it, so it also has to be rewritten. This could be rewritten as 2x to the 1/2. Okay, so according to the power rule, the 1/2 comes down in front. The constant multiple rule tells me to multiply those two numbers together. 2 times 1/2, or 1. I'm then going to subtract 1 from the exponent. 1 minus 1/2. I'm sorry, 1/2 minus 1, which is negative 1/2. This one can be rewritten as 1 over x to the 1/2. Some students also prefer to write that back in radical form. That's going to be your own personal preference. So just as an option, an alternative way to write this would be 1 over the square root of x. You choose. Finally, for this rule, a pretty complicated equation. When we rewrite it, the 2 that's in front here needs to stay down there. So this will be written as 1/2. That radical needs to be changed into a negative exponent. This will become x to the negative 2/3. Now remember, again, we haven't done any calculus yet, so this isn't y prime. This is still just y equals. Now I'm going to actually do the power rule. 1/2 times negative 2/3. It's a little bit harder to do the mental math with this one, so I'm going to go ahead and write it out. And then subtract 1 from the exponent. Some students have trouble doing this mental math in their head as well. Think of it when you subtract 1 with a common denominator. So I'm really going to take negative 2/3 minus another 3/3, or 1. In that case, the answer would be negative 5/3. With some reducing, these 2's cancel, and I get negative 1/3 x to the negative 5/3. Or negative 1 all over 3x to the 5/3. The last rule we're going to do is the sum and difference rule. This is what's going to actually put all this together for polynomial functions. What it says is you can actually add or subtract two functions, f and g. Then the answer will be the derivatives of each one of them separately. So you can add them or you can subtract them. Okay, here's some examples of this. First one, f of x equals x cubed minus 4x plus 5. For the derivative, f prime, the first term, x cubed, the 3 drops down in front, and I'll subtract 1, then minus 4 times the derivative of x. And we said that's a special case. X turns itself into a 1. And finally, the derivative of 5, well, 5 is a constant, so that's just plain 0. Officially, this derivative is going to read 3x squared minus 4. For the next one, g of x equals negative 1/2 x to the 4th plus 3x cubed minus 2x. So for g prime, the 4 drops down in front, subtract 1 from the exponent, plus, now the 3 drops down in front. 3 times 3, that's 9, subtract 1 from the exponent. And finally, here's this special case, x turns into a 1, so I'll have just plain minus 2 times 1. All cleaned up, the answer should be negative 2x cubed plus 9x squared minus 2. It's my goal for you not to have to show any work for some of these problems. Some of them, when you rewrite, yeah, it's probably a good idea. But with these polynomials that have nothing to be rewritten, you should probably try to just go with the answer. See if you can do that mental math in your head, those fractions, the subtraction. The better you can get at those skills, the faster the rest of the work will go. So here's a list of all of our basic rules that we have so far. If you haven't already, go ahead and make sure these are jotted down somewhere with a couple examples to help you practice. Next thing we need to look at is derivatives of trig functions. At this point, you're required to know two separate ones, the derivative of sine, which is cosine, and the derivative of cosine, which is the opposite of sine, or negative sine. These come directly from the mathematical definition of the derivative. Someone has already gone through with the limit process and come up with these using some special trig identities and some special trig limits. Just to show you how this works, let's look at these two examples. Trig works a little bit different. Instead of moving exponents and changing numbers, we just do a direct replacement. So here, for the function y equals 2 sine of x, I'm going to go straight to the derivative. 2 is a constant, and it's a multiple, so it just gets multiplied in. And sine gets directly replaced with cosine. And that's the answer. Down in the second example, I've changed the x into a theta. That's because usually when you work with trig, the values are typically angles. So you'll see theta a lot. This is just like an x. It's a variable. So, since theta is just like an x, a variable, its derivative is also 1. The memorized value of cosine is negative sine. So this derivative could be written as 1 minus sine of theta. So again, at this point, trig is a direct replacement. You'll learn the other 4 trig values later on. The last thing we need to learn how to do is to write equations of tangent lines. Here's a quick example of one. In this one, you're supposed to write the equation of a tangent line to the curve y equals x squared plus 1 at the point x equals 1. Just to get a visual representation of what you're actually doing, Here's a quick picture. This picture shows the function y equals x squared plus 1 and some tangent lines drawn at various places. Remember, we're most concerned actually only concerned with the value here at x equals 1. So that's the equation I want to write. Not an approximation, but an exact equation. To do that, we need to use some algebra first. All equations start with y equals mx plus b. They have a point, an xy coordinate, and then a slope. To find the corresponding y coordinate, I'm going to use the original equation, y equals x squared plus 1. Substitute 1 back into that original equation like you would in regular algebra. So y equals 1 squared plus 1, or 2. Easy enough. The next part, however, is going to require calculus. In order to find the slope of a tangent line, we use the derivative. That's the whole purpose of calculus at this point. So I'm going to need to actually evaluate the derivative. Here in this problem, the derivative of x squared plus 1 would be 2x plus 0, or just 2x. The slope is actually going to be the derivative specifically at the point 1. The notation we use for this is f prime of 1. So I shouldn't see any x's in this answer. This is a numerical value, an actual slope at that point. Well, by substituting 1 into the derivative right here, I get 2 times 1, or 2. Again, this is the specific slope at the point x equals 1. It's different everywhere else. But now I have enough to actually complete the problem. Y equals mx plus b can be written as the y coordinate 2 equals the slope 2 times the x value 1 plus b. Just doing a little bit of algebra, I find out that the b number, or the y-intercept, is 0. So the equation of my tangent line is y equals 2x. That's different everywhere else. And there it is. Just by visual inspection, you can see that we must be right. This line does go through the y-intercept of 0. It goes through the point x equals 1, and the corresponding y-coordinates 2. By counting blocks, I see that it's a slope of 2, up 2 over 1. So everything looks good. All right, this concludes all of the basic rules we're going to learn today. As we go on throughout the chapter, we'll keep adding more and more for more complex equations. For now, though, we need to get these to be automatic skills. So we're going to practice a lot in class tomorrow.